So in this section, we study higher order derivatives. Suppose omega is an open subset of Rn, and f is a function defined on omega. So we have defined the partial derivative. So if for every x in omega, the partial derivative of f at x with respect to the ith component, that is dIf(x), exists. Okay, for every x we have this partial derivatives. Okay, then we obtain a new function from the given function f. If this condition is satisfied, we have a new function. This function also denoted by dIf, which is a function defined in omega. How this function is given? For any x in omega, because the partial derivative exists, therefore we can associate to this x the value of the partial derivative. Okay, so the value of this function at the point x is the partial derivative of f at x with respect to xi, or the ith component. So we have this function. This function is called the partial derivative function. Okay, this is the partial derivative function. The definition of a partial derivative is concerned about a point A, concern the partial derivative at this single point A. But if at every point you have partial derivative, you will get a new function, the partial derivative function. Now we can consider whether this partial derivative function has partial derivative. Okay, so this is the definition. If this function defined in omega has partial derivative which respect to the j component, that is to say, at the point the partial derivative with respect to the jth component at the point A, at some A in omega. What this means? This means this exists. Okay, if the partial derivative function has partial derivative with respect to jth component at the point A, if this exists, then we call this is the second partial derivative of f at A. We denote this by dij, maybe dji, which is here is the partial derivative function. If the partial derivative function has partial derivative with respect to xj at this point A, then this partial derivative is called a second derivative of f at A. More precisely, a second derivative, first derivative with respect to xi, then xj. So the derivative taken for xi first, then followed by xj. Okay, so this is the definition of second order partial derivative. Of course, here I and j, here I can be 1, 2, or n, and the j is also can be 1, 2, n. Therefore, we actually have n square second order partial derivative. Okay. So for second order partial derivative, as we just introduced this concept, as we say, it is we also use other notations. For example, we can also denote this by so here the inner part of this is the partial derivative function with respect to xi. Okay, then we take the partial derivative we take the derivative with respect to xj for the partial derivative function at this point a. Okay, so this notation is classical. This is the classical notation. We also write this as at the point a. Okay, so this is the later two notation. In particular, the last one is classical notation. But it will be more convenient to use this notation at the first two notation. In particular, the first one. You should take care of the order of ing. Okay, and we also use another commonly used notation that is Fij. We also use this notation to denote the derivatives given at the first line of this page. What's this? This you can consider this as the partial derivative function with respect to xi, then take the derivative with respect to xj at the point a. Therefore, Fija is in fact djif a. You should take care. Notice the order. Okay. So this is the second order partial derivative of our function at this point a. Now, here we talk about a point a. If the second order derivative exists for every a, right? So if djif x exists at every x in omega, what will happen? Of course, associate x to this partial derivative of f, second order partial derivative of f at the point x. This gives us a new function defined in omega. So this is a new function. Defined on omega, right? So this function we denote by djif. Okay, this is a new function. The value of this new function at the point x is precisely the second order partial derivative dji at this point x. Okay, so this gives us a new function. Now, if this new function has partial derivative, if this new function has partial derivative with respect to the kth component or xk, at the point a, what we will get? We have dk djif. So this is the function we are taking partial derivative with respect to the kth component. Okay, at the point A, we have this. We have this. This is a number. This is the partial derivative of the second order derivative function with respect to xk at the point A. Okay, so this value, this is called a third order derivative, partial derivative of f at this point A. Okay, so as you can guess, denoted by we use this notation dk GIF A. Okay. Of course, if you use the this style of notation, F sub index notation. If you prefer that notation, you can write as F I J K A. Okay. So this is the third order derivative. Okay. So in this manner, we can define again we can define arbitrary order of partial derivative. Okay, so we have if f is a unvaluable function defined in some omega is a subset of Rn, then such an f will have n to the power k kth order derivative. A typical one is DIEIKF. Okay, or you can write FIK minus 1 I1. That is DI1 IKF is the partial derivative with respect to I1 for the function, for the partial derivative function k minus 1 order I2 IK. Okay, this is the D notation. If you use this style of notation, then the same thing happened. FIK I2 I1 is the FIK I2, the I1 with respect to I1 partial derivative of the FIK I2. Okay, so of course you can use the classical notation. The classical notation of a kth order derivative is this. DKF dx I1 dx I2 dx IK. Maybe we have solid I1 here, dx I2 dx IK. Okay, so this is the classical notation. I remind you that xi does not mean the power. Xi is the ith component of x. Okay, this is our convention. the index of component we write as a superscript. So here the I1, I2, IK here does not mean do not mean the power, but the I1, I2, IK are the index of components. Okay, so what this means? This is precisely the partial derivative with respect to xi1 for the k minus 1 order derivative dk minus 1f dxi2 dxik. Okay, so the last line is the classical notation. Well, these two lines are modern notation. They will be more convenient in application. Okay.